Well, I work for Jet.com. I'll tell you what Jet.com is, but that's the unimportant part, right? Yeah, so I live in New York, just officially on a vacation, by the way. No, it's okay. This is not official, right? It's just so I want to make it more like an interactive session than actually being a lecture, right? So if I speak too fast, I know a lot of people here are not native English speakers, so if something is not clear, please feel free to interrupt me. I can slow down, repeat myself. Not a problem. Okay. So I'm going to talk about how we implemented, event-driven microservices architecture in a functional language. I try to make that talk not too much specific about F# and more about functional programming, because a lot of concepts that we use in F# can directly be translated to Scala or, for that matter, in the language. So a lot of what I'm actually going to be talking about will be more generic, that something you guys can actually go ahead and use irrespective of what platform or language you actually use on your day-to-day work. So I'm going to give you a little bit of background about Jet.com. I'm going to talk about the technology choices that we had. We had some unique technology choices, obviously. Some lessons that we learned about what were the issues that we faced when we used a rather unconventional language like F#. Most of the people don't even know what F# is, FYI, so I'll probably have a slide on that also. The lessons we learned, the advantages we get, and so and so. Okay. I'm going to be in the middle, so I don't block the slides on either way. Okay. So let's actually get started. So I'm going to start with the background of what Jet.com is. So we were launched in July 2015. We were acquired by Walmart it was announced last August. The official acquisition happened in September for $3.3 billion. We were the biggest acquisition ever to happen in e-commerce, one of the fastest companies to go to $1 billion. They call it unicorn in States. I don't know the terminology in German, right? But unicorn is basically a startup with like market valuation of over $1 billion. So we were one of the fastest unicorns of the world. And I have some numbers here. My purpose of having these numbers here was just to give you guys an idea of the scale at which we operate, right? So it's it's one thing as designing a service for like 50 users, is another thing as designing a service that has like 5 million or 10 million, right? The technology choices and the trade-offs you have are completely different. So we have a dynamic pricing engine, which in short, what it does is, as you shop, it actually optimizes what would be the cheapest way for you, what would be the cheapest alternative for you to procure goods. And in this dynamic pricing engine, we have about 2 million calculations that are actually happening every second. So for that, we actually use a specialized GPU to do that, because you don't get that out of the cloud. We have about 8 million customers. We have 25,000 orders daily, and last I checked, there were 15 million. This number is actually very quite screwed, because this was the Jet inventory. Now that we have merged to Walmart, our inventory is like orders of magnitude more than that now. That fine. Okay, so we technology stack we actually run on Microsoft Azure, and there was a business reason why we decided we compete with Amazon. So the last thing we want is to build our system on top of AWS, right? So that was why we chose Azure, which we are probably one of the biggest users of industrial Azure. And now Azure is quite open, but at that time, JVM was not very well supported. For us, .NET was actually the way to go on Azure. So we decided to use, we had .NET framework, we have a mix of technology, Kafka, Redis, Splunk, and so on. And the backend we have is in a language called F#, which is a functional language derived from OCaml that actually uses object-oriented model from .NET. Actually, when we started, the history was that they started with C#. They did not start with F#. They built the first prototype with C#, and some of the engineers, some of the early engineers, one of them, I think you pointed out in his talk, he actually knew F#, and he was like, let's actually try building F# and see if F# is better. And they then rewrote the initial app in F#, and turns out that the advantages in terms of speed, in terms of developer productivity, just was like phenomenal. So they just scrapped all the C# code and rewrote everything from F#. So people think that we are a functional shop. Well, we are now, but when we started, we weren't. So anyway. So architecture, right? So what are, how do we design our services? So we use actually heavily domain-driven design to design our services. Domain-driven design is basically, for those of you know, I think it's pretty common. For those of you who don't know, it's actually a software development methodology that connects the implementation of a system to an evolving model. And I'm going to talk more about it. We use event-driven architecture. In short and simple term, event-driven architecture is you have an event, you react to that event. Event sourcing is basically a paradigm where rather than storing the state of your system, you actually store individual sequence of events, right? And you basically build the state from those events. Knowingly or unknowingly, almost all of us use event sourcing every day. For example, when you go to a bank, you're using event sourcing because the way bank looks at it is you have transactions, right? I put some money, I withdraw some money, and so on. And your state, which is the money you have in your account, is nothing but a sum total of all the events, basically sum total of all the transactions, right? Your version control system is an event sourcing system, right? Git. Because when you're committing a series of delta, and the Git basically combines those delta. It has obviously a whole lot of algorithms to optimize all these things, but essentially what you're doing is summing up all those deltas in one particular way to get your source code view. So that's another example of event sourcing. And we have a microservices-based architecture. I don't really need to explain what microservices is for the sake of completion, and these were the slides I took from another presentation, so that was just there. Okay, so now let's actually talk about domain-driven design, what domain-driven design is. So as I said, domain-driven design is basically an implementation methodology where you connect the implementation to an evolving model. So there you have a concept of what they call as ubiquitous language. Okay, so ubiquitous language, what it is it is a language that is how do I explain it the right way? A sort of a DSL, domain-specific language, right? So the terms you use are basically you represent your domains and you talk in terms of those domains. For example, banks will have customers. You don't talk about like software, right? You build a model out of your domain elements like your bank account customers. In our case, it will be customers, items, indexing, shipping, all this stuff. And there you have also a concept of bounded context. So what happens in real-world systems, often people think that we will build a model of the system, but real-life systems are so complicated that you cannot have one model for everything. So rather than having one model, you have a series of smaller models. Each one of them is called bounded context that connect together. And then you have a concept of aggregates. Aggregates means things that you can treat as one object. So your domain might be made of subdomains. For example, think of a shopping cart, right? Shopping cart has items, prices, and all those things, but you can treat the shopping cart as one entity. So these are some of the concepts of domain design. There's actually a very good book written by Eric Evans, Domain-Driven Design, same title. It's a thick book, so it's a good book if you want to read, but it's a really 500-page thick book. There's another book called, I think, Domain-Driven Design, distilled by Vince Wong. Gives you pretty nice reference about what domain-driven design is. So boundary context, right? You have different kind of models, and then they are connected through schemes, queues. In this case, front end, and so on. So another very common pattern with domain-driven design is CQRS, Command Query Responsibility Segregation. That's what it stands for. So what it says is that in your function, you should have read and write separate. So for example, let's look at the right side of the slide, right? Customer service. You have my right, okay, sorry, your left. Okay, your left side. You have all these operations, and you see some of them actually make changes to your state, some of them return something. And what CQRS says is segregate that into a read and write. And read service will just give you back some objects, and the write service will change the state of the system but won't return anything. They might return an acknowledgement if the operation is successful or not, but they should not return an object. And then what you can do is you can scale out read and write separately. There's a reference about CQRS. It's actually a pretty common pattern used. I think the originator was Greg Young, and I don't know when it actually emerged, but it allows you to scale the scale read and write independently, because what happens is that often your system has like too many reads and very few writes. So you don't want to tie them together. Okay, so there are different architecture models of domain-driven design. This is probably the most simplest one. They are more complicated, like hexagonal, onion, and so on. But what domain-driven design is that it divides your application into 4 layers, right? The user interface is actually pretty simple, right? It's typically your front end often runs in the client browser. Then you have the application layer. Application layer is mostly handles the transactions and so on, and this is often a thick layer. The bulk of your code actually is in the domain layer, and domain layer is where you have your basic domain objects, right? Or in the DDD terminology, it's called value objects. And then you have the infrastructure layer. Infrastructure layer deals with your disk, I/O, and so on. The persistence layer. Typically, infrastructure layer will be dealing heavily with the side effects. But the bulk of the code is in domain layer, and domain layer, as per DDD, should be immutable. So DDD recommends the value objects are immutable. And where we find is that while DDD process had nothing to do with functional programming, it turns out that functional programming is a really good paradigm to implement DDD, because immutability is something that is built in, right? So you can have value objects. In F#, you actually can attach member function, and I'm pretty sure you can do the same in Scala. You actually can do the same in Scala, right? Scala calls it extended, what is it called?
Implicit?
Sorry?
Implicit?
No. Scala's pattern matching happens through, I forgot the term, case classes. Yeah, Scala has case classes, and you can attach member functions to scale classes. So how you would implement a DDD in a functional language is you would model your domain objects as abstract algebraic data types, right? Whether if F# discriminated union or Scala case classes, whatever language you're using, and then you would attach member functions. So those values should be immutable, but you can attach member functions and return new values, of course. So that's how you would use functional programming in a DDD context. And there's one pattern that typically you want to avoid. It's called anemic domain model. And anemic domain model means your value object, your functions attached to those objects are nothing but getters and setters. So, very often when people implement DDD, they usually will have some class, and they'll just have getters and setters to get those value objects. But you actually should have member functions that would do bulk of operations attached, and not just simply getters and setters. So anyway, so functional programming can actually be very, very effective in implementing DDD architectures. Okay, so event-driven architecture. What is event-driven architecture? It's actually pretty simple, right? I mean, if you read the name event-driven, events are essentially driving your architecture. So events occurs when a change in system happens. In terms of e-commerce, I'm ordering something, I'm adding an object to my cart. If you're talking about some rental service, I'm renting something, I'm returning something, they're all events. The characteristics of events are that they are immutable over time, right? An event happened that you purchase something at time t1. This happened, this cannot change. If you return that same thing, that's a different event, right? Because it's happening at a different time point. So at T2, you might return something that you purchased at T1. So they are two separate events. So event by itself is immutable. And event-driven architectures, you would have a producer and a consumer. A very common example of event-driven architecture is Kafka, right? You have the consumer and the producer, you have the broker in between. So
The typical characteristic of event-driven architecture is that the producer does not have knowledge about who's going to consume the events. And consumer, often, you can have multiple consumers, listening to, or no consumers for that matter listening to, and it's a very highly distributed and loosely coupled architecture, right? Whereas you use asynchronous method of communication. In everyday life, you use a lot of event-driven architecture. One of my favorite examples is if you're at the airport, right? Somebody's announcing a flight is leaving Munich in half an hour. That's an event. He's making an announcement, right? So he does not know who's listening to it, right? In this case, the intermediate broker is nothing but a microphone system or a speaker, an ear, whatever. And you as a customer receive that event, and then you know whether you want to react to it or you can just ignore it. And the listener is not aware of how many consumers are there, right? Consumers can be dynamically added or subtracted, but the system by itself is very highly distributed and still work fine. So event sourcing. I talked about event sourcing. The state of the system is stored as sequence of events, right? And the big advantage that an event sourcing can do is you can go back in time. You see the same thing, let's say if you're using a version control system, right? You can see each of the individual commits that you have, and you can go back in time and say, okay, I want to roll back my code to what it was on, I don't know, maybe 1st of April. Right? Not the best choice of day, but sure. So event sourcing enables you to roll back to a particular time. You can combine and recombine those events in any manner, and that's a very big advantage with event sourcing. For example, let's take a bank example, right? You make a series of transactions, and you decided that the 10th transaction on your credit card basically was a fraudulent charge and you wanted to remove it. So you remove it, and you can recombine all the events that happened after it to create a new state. If you were storing the states, not the events itself, but the states, it's very hard for you to do it. You could possibly do a delta across the state to see the event, but the advantage of event sourcing is you can take these events and combine and recombine them in any fashion. So here's an example. Another very common example, this one is basically something similar to Facebook. So if you open up Facebook, you have your personal info section, you have your photos, and you have your timeline. You add events on your timeline. Events happen, and different applications react to these events in different manner. For example, you got married. So you have on your timeline, ABC got married. On your personal info section, it receives that event, it updates your status from single to married. Your photo receives that event, ignores it. You post a photo, timeline posted. The personal info section receives a photo, does nothing, ignores it, and the photo section adds that photo. So the characteristic of event sourcing is that you have these different applications that process the same event, and they can create different views of it. Right. So typically you would do that in a social network. Any questions so far before I proceed? Okay, so for the sake of completeness, I've added a slide on microservices. I'm not going to go and explain what it is. Everybody knows about it, I'm assuming. And if you don't, then I don't know if you should be here. Okay, so microservice architecture, kind of the same thing, right? You have different microservices running each in its own process. We have about 1,000 microservices in production the last I checked. It's not uncommon to have these numbers. I don't know, I guess you also use, at Autoscope they use microservice architecture. I know Uber, I was talking to a guy in Uber and he mentioned they have about 6,000, 7,000 microservices running in production environment for them. Okay, so again, this is common. I don't need to explain too much, but some of the common advantages of microservices, you have independent releasability because the teams, they can be independent, they don't have to depend on each other in a monolithic world. You deploy everybody at once. You have technology heterogeneity. I know I was talking to Krishan about the same thing. Some services are running .NET, some services are running Java. It's okay. or Scala. It's still okay. You still have resilience built in the system, right? Some of the services, they stop working, the rest of the services still continue to work. It's not that one bug is going to bring the entire application down. And last but not the least, terms of migration, which, tech stack is going to be rewritten every couple of years, whether you like it or not. So this is actually a very major advantage with microservices, that you have the ease of migration. Okay, so you have typically two different deployment patterns in microservices, right? You have a request response one, and you have an event driven one. So in a request response, you have the diagram, it's pretty easy. You send a response, you get a response back. It's a synchronous way. The advantage is that failure modes are very easily happen. Like in an event driven, you send an event, you have no way of tracing that event, right? By definition, that event can trace. Whereas in a request response form, you have a traceability for your call. You're going to get back a response, 400, 200, whatever the response is. So error handling tends to be really good. The problem with request response is not scalable. Whereas in event driven, you have like a lot of scalability. You can add and subtract more services to your broker. So how these patterns are used is, typically you have 3 tiers of, so you can have n tiers, but usually 3 is the most common. Now in our case, we have tier 1. Those are the services that are, if they go down, the customer is directly impacted. For example, the front end jet.com, or front end of your website, right? It goes down, customer cannot use. Tier 2 services are services that they would impact the customer, but not in a severe manner. For example, your order management. Customer places an order, fulfillment service is now fulfilling. If it goes down for 2 hours, well, your order is going to be delayed for 2 hours. It's not like it's gone, you're like helpless and so on, right? It would impact you, but not in a severe manner. And then you have the tier 3 services, where your telemetry, monitoring, and so on, right? If your monitoring system goes down, as long as the rest of the services work, you're fine, right? It doesn't really impact the customer. So how we do it is, we typically use request response on the tier 1, because we want very high error handling capability in tier 1, whereas tier 2 and tier 3, we tend to do more event driven. So that's how the deployment patterns fit in. Questions?
You mentioned that REST API is not scalable, right?
Yeah.
Why it's not scalable? What stopped you from running 1,000 copies of your REST service?
Okay. So the question was that I mentioned the REST API not scalable. What stops me from writing properly? Well, here's what. I can do that, but let's say if I want to add another service, right? I have to change a lot of other services also. So, for example, I want to add a new service here, right? At this, can you see the pointer here? I want to add a new service here. I can't just plug in that service. I have to change this one also. In a more complicated network, this is a very simple picture, right? But imagine a big graph. You add one node, you have to change several edges. That's the problem. You can do it, but it's a big change. Whereas in event-driven, you have the broker, you just plug in a service, your producer does not even care about it.
But, it's the same with event drive, because if I change my model of my event, so I have to change listeners and...
Yes, but typically you don't change your model of events that much. Yes, if you change even in microservice, the same thing as if I change a microservice contract, that's a big change. And then the whole microservice is, yes. But typically that's not what you do often. You shouldn't be, right? Typically what you do is, well, you have an event, I want somebody else to process it in a different way. You have a question, Christian?
Yeah, I would rather say it's not about scalability, but about evolvability. So it's easier to evolve there and add or remove services than in a more coupled fashion, because scaling typically means scale out, and adding additional services is doable in both cases.
Yeah, so maybe I'll use a better choice of word. Request response is a tightly coupled model, whereas event driven is a loosely coupled model. And that is why maintenance and evolvability would be affected. Okay, don't look to be convinced, but yeah, you can talk afterwards about this. Everybody has his own comments, so I'm not like offended by it. Okay, so let's actually get into a little bit of the functional stuff. But when you look at a microservice, or for that matter, any service, right? It's nothing but a function, especially in event-driven one, right? You have an input event and you have an output event. Mathematically, it's a function. Most of the services tend to be pure services. Pure services means you don't have any side effects, with the exception of logging, right? Logging does not alter your system, so I won't consider logging as a side effect. And then you do have some of the impure services where you have a database or some other I/O side effect, and there you have an input state and you can represent it in a different way, that when an event happens, it alters your input state to create another state, output state, right? So you can mathematically represent why an output state is a function of input event and input state. And before I actually talk too much about functional programming, I'm actually going to sidetrack a little bit and question the reasoning of using object-oriented programming. So let's actually get down to a little bit of a history. When you look at programming models, right? Today morning I was actually in the Deutsche Museum and they showed all the early ones, Mark 1. So this is actually pretty relevant because I just did a refresher course today morning. So in the morning, so when you look at these early architectures, right? They're basically modeled as Van Neumann architecture. And Van Neumann architecture simply says that you have a memory, right? And you manipulate that memory. And early programming languages, imperative languages, were built and they were closely tied to Van Neumann architecture, right? Because hardware was really the expensive part, software was easy. And when you think about C and Fortran, they are basically, what they are doing is you have these variables, right? And you manipulate those variables. And variables represent location in memory. So essentially, variable basically represents a state of a system. And you hop from one state to another state. In simplified form, you can think of it as a state machine and so on. And this model worked very well for 50s and 60s. And at that time, there was little to no internet and there was no issue of portability and all those things that worked, right? This was way back then. And then as the complexity of the software grew, we started with object-oriented programming. So C++ was one of the, not the first one actually. C++ came because C was the dominating imperative language, and Smalltalk was a very popular object-oriented language. So the inventor of C++, I'm not sure if I'm pronouncing his name correctly, but James Strausstrup, he combined the Smalltalk model of object-oriented into C and created what was called as C with objects, which was later renamed to C++, right? But essentially, object-oriented programming is built on imperative languages, and there are two important concepts: the concept of encapsulation and concepts of polymorphism. Encapsulation, because you have a class where you have private and public, and you can manipulate the public part, but you can't. The private part is kind of hidden from hidden from the rest of the code other than the class. So there's an encapsulation there. And the second problem is that you have this concept of inheritance. So you can have one interface and you can have multiple subclasses that inherit that interface, and you can use that one interface commons across all those classes, right? Typical toy example, you have a shape and you calculate the area of the shape, and then you have the subclasses, square, circle, rectangle, whatever, and correspondingly it just operates on those individual shapes and so on. But object-oriented programming was still very much tied to Van Neumann architecture, right? And then something happened suddenly in 90s, and there was this thing called internet. And it suddenly brought two problems that at that time the languages couldn't solve. That was A, portability, and B, security. All right. So new classes of languages were built. Historically, Java was called Oak, and it was actually being used for consumer electronics. And then Sun actually, they renamed it Java and targeted towards internet. It wasn't actually originally built for internet. And then later on, Microsoft came up with their own C# managed languages, which some say is Microsoft's version of Java, although it's a very highly debatable topic by its own. Microsoft denies that, FYI. I know I used to work for Microsoft, I can tell you that part. So what happened as a result of it was that object-oriented programming became like the de facto way of programming. Right? This is, if you want to program, that's how you program. But if you look closely, object-oriented programming was originally built for Van Neumann architectures. Web services don't run on Van Neumann architectures. Web services typically run on your virtual machines, JVM or .NET framework or whatever you're using, right? That does not deal with memory directly. It kind of abstracts out all that memory handling for you. So there's kind of a gap here. Like is object-oriented programming the best way to deal with systems that are not directly manipulating Van Neumann architecture? And I would question that that's not the best way out. So what we found was that when you're talking about web services, microservices, or even for that matter monolithic services, functional programming is actually a very, very effective way, effective means to implement that. And the reason is that your physical concepts get actually mapped to programming concepts very naturally. So again, object-oriented models, they store your applications as object with states, whereas microservices actually don't have states. So why would you use object-oriented, right? Imperative encapsulation, sure, you could possibly use it, but you don't deal with Van Neumann architecture. And there's one advantage that you have, that OOP languages tend to have very good ecosystem. With languages like F# and Scala, right, they're fully interoperable with .NET framework or JVM framework. So anything you can write in C#. In fact, in our code, which is predominantly F#, if you look at all the third-party libraries that we are using, they're all made for C#. I mean, we can download the code and see they're mostly C# code. So you can seamlessly operate that. So you can take advantages of the very good ecosystems of Java, C# in F# Scala. Questions? No. So, continuing the argument, why is functional paradigm so useful in web services? Like I mentioned, your physical concepts gets mapped to the paradigm concepts very naturally. In services world, what you call a service in a functional world is nothing but a function, right? Y is equal to fx, as I showed. And when you look at events in functional programming, you have algebraic data types that can model these events very well. Scala has case classes, F# has discriminated unions. I don't know the name for Haskell. OCaml also has discriminated union. Haskell probably has some other name, I don't know the name for Haskell. Stepping aside, when you think about object-oriented programming, when I was at Microsoft, I did a course that they make you do. And it was about debugging. So the instructor said, 3 most common reason why your code does not function as memory. And what he's trying to say is that your system enters a state that you did not account for, right? And then it doesn't know how to get out of it. Why does that happen? The reason why that happens is, imagine you have, let's take a simplified when you have a code with 1,000 classes, right? And let's for a moment assume that each class has 4 Boolean variables, right? So how many permutations and combinations we are getting right? 4 to the power 1,000, right? Sure, you have error handling and so on. Are you sure you have error handling for 4 to the power 1,000 cases? And this is a very toy example here. The unfortunate part is your real world code is going to be much more complicated than this, right? So if you can't take care of 4 to the power 1,000 cases, are you really going to take care of what's going to happen in your real life? So typically what happens is that system enters a state that you did not account for and it crashes. And this is the state space explosion that object-oriented programming actually has a severe drawback on. And what you can do with functional programming is, there are other things like immutability that I'm going to talk about later on in the talk, but what you do with functional programming is you can model these events as algebraic data types. So you can limit, right? So you're going in an exponential series here. So you can limit the possible number of states that system can enter. And if you can limit the possible number of states that system can enter, then assuming your compiler is bug-free, system won't enter into that state. And if system won't enter into that state, the chances of errors go drastically down. So algebraic data types are actually very useful in such that you can have these events and you can model these. So we'll see some examples later on. You can model these events as algebraic data types, right? And then you have events that are immutable, and because we can't go back in time and change it. And functional programming actually has immutability built in. The statement is actually not 100% true. Most of the functional languages do allow immutability, and I'm going to talk separately about that. But if you follow the functional paradigm, you're supposed to have immutability. They do immutability. They allow mutability because they have to interact with Java and C# and underlying frameworks. And for compatibility reasons, they have to. And in certain cases, mutability actually makes a little more sense, especially if you're dealing with your I/O and transaction and data layer and so on. But generally, functional paradigm and languages like Haskell tend to be pure. So in their case, the immutability is absolutely enforced. And then you have the services world where most of your services, not all definitely, are stateless. And in the FP world, most of the code you should write, some people don't, but that's the proper way you write it, is a pure code, right? When I write a code, I could count on my fingers how many mutable variables I use, and most of the time it's 0. So my purpose of putting this slide is that functional programming captures the behavior of service architectures very naturally, that you could pretty much have one-on-one correlation with the way you physically imagine that and how your code would implement those concepts. Questions, if any? Right. So I'm going to get to what F# is, right? I didn't know you guys use Scala. I could have added a slide on Scala. Sorry about that, but I'll still talk about Scala. So F# is a function language for .NET, and how F# evolved was, I'll give you a little bit of history of which is not covered in the slide. But the guy who invented Haskell, Simon Peyton Jones, he was a professor in, I think, Glasgow University, left the university and joined Microsoft Research because he wanted to bring functional programming to masses, and he thought that there's an opportunity at Microsoft where if you can make those languages that fast, you could potentially scale it up for masses. At the same time, Microsoft was releasing, it used to be called something like Next Generation Platform. I don't remember the exact name, but what we call is .NET back in those days, and we're talking about early 2000, right? It used to be called the Next Generation Platform, and where the thought was they can integrate Haskell with that platform, and that way people can just code. You have excellent third-party system, and people can just, and Windows used to be the most dominant operating system at that time, right? Not probably anymore, but you can use Haskell for real-world programming. And they ran into problems. They found that the Haskell couldn't really, the model, they couldn't really find a good expression for translation to .NET. So they switched to OCaml. They said, okay, let's try OCaml here. And then they finally created a language that combined OCaml with .NET classes, and that language became what is called as F#. Right? And this happened, I think the commercial compiler was released with Microsoft 2010 Visual Studio was released commercially, but experimental compilers were released as early as 2005. And I think Scala was also born around the same time, give or take a few years, so they sort of have a parallel history. So F# is basically a statically typed managed functional language for .NET. Statically typed because you have types, statically typed well-known. these types are taking like compile time. Managed is a term we use for any language that is on the .NET, in the sense the memory model is managed for you, whereas C++ is kind of native. They don't use the term managed, they use the term native. So you have like the native languages, and then you have the managed languages, and there are some languages that are in between 50% native, 50% managed. So F# is completely managed, right? There's a declarative style, there's immutability, functions are a building block. Practically most of what is true for F# actually is also kind of true for Scala. Scala also started along the similar lines, that they wanted to bring the functional programming to the Java world, right? But they didn't want it to give up completely on the O layer. So when you look at languages, in real life, we may think of functional language and object-oriented language, but in truth, real life it's a spectrum, right? And if you put functional as one side of this and object-oriented to another, Scala is something like in between, 50-50. F# is something like 25% object-oriented, 75% functional. Haskell would be 100% functional. Like Haskell does not give you any other choice. You have to use, it's a pure language, you have to use functional paradigm. And if you think about C#, and now I think Java 8 supports Lambda functions and so on, they probably will be like 10-20% functional. C# probably more, 30% functional and 70% object-oriented. So what we see now in language designs is that people tend to take the best ideas from whatever paradigm and implement it. And I won't be too surprised if Java would someday support pattern matching. C#, the new version of C#, 7.1, 7.2, it actually does support pattern matching in a limited manner. And I think C# 8 will probably incorporate it completely. But often what happens, and most of the real-life systems are also hybrid, because you have to interact with your application layer, you have to interact with your data, you have to interact with your DB. They're all, I/O is essentially a side effect, so you do need the capability to deal with side effects. So F# is a language that is designed in a way that is predominantly functional. It allows you to use impurity, but you have to fight with the language, right? And the reason why they did it is, they did it on purpose, that at times and places where you have no other choice, you want to use, and you're doing some I/O, you want to use a side effect or something, put it. Fine. We'll make it difficult for you, so you only use it when you need it. You don't use it when you don't need it. If you make it too easy, then it leads to abuse of language. And I was talking to one guy actually in London, the last conference I presented this talk. It's like, you'll be surprised that most of the people, the vast majority of people I know who use Scala, they just abuse the language badly, right? And the problem is that when you give people multiple ways of thinking, right? Multiple ways of, C++ is horrible in that for everything you have 5 different ways of doing it. And then you create confusion and it leads to abuse, right? So you want to prevent that abuse from happening. So F# does it in a beautiful way. Scala, I don't want to criticize the language, but relatively is more complicated in the sense it supports a lot of different paradigms. So it could be confusing at times. I'll look at some examples of F#. So let's switch gear to microservices, right? So you have a function, right? You have an input and you have an output. And in event-driven world, they're both events. So how you typically would implement is, you will model your input event as an algebraic data type. You model your output event as another algebraic data type. And then you carry out an implementation. For example, here you want to search an item. So you want to search it by an item ID, SKU number, or you want to do it by name. And then output is, the item is in inventory, I can give you a count. Item is not in inventory, but I possibly could give you a date when it would be, or we don't carry that output. And then you will have a function that maps this input events, this output events, right? So in the object-oriented world, what they teach you is that when you actually are implementing an OOP, especially in C++, you tend to write headers of all your classes, right? Let's not write the functions right now. Just write the inputs and outputs, just write the headers, right? UML will teach you the same thing, write all the functions. And then you can go about implementing them. When you do, this concept also sort of applies in functional programming. When we do functional programming, we do the same thing. The first thing when I write my functional program is I write all my types. The second thing I would do is I would write one-line function x takes type of A, output type of B equal to not implemented. I'm not going to implement those functions, right? My blueprint of the software is nothing but a mapping from one type to another type. Like blueprint of object-oriented or architecture of an object-oriented program is nothing but all your class hierarchies, all your probably not private, but at least public functions and public properties of a class. So in functional, you would do the same thing. You would just map the input output, and then you implement the code. Questions? All right. So there are cases where you want to use asynchronous workflow. You typically won't use it too much because if you're using an event-driven architecture and using Kafka, then Kafka kind of does that for you. But here's an example. You have different services running, right? So you create an async workflow, you create an order, you return an acknowledgement. So stock service sends an async request to ship, so that happens in the background and returns an acknowledgement to the order service saying, hey, I've synchronously received, I've sent the request and it's fine, okay, 200, whatever the code is. So anyway, so we in our code base do a lot of static analysis of F#. Now, the problem of using F# that it's not a mainstream language. Scala is relatively, I think comparatively, Scala is better than F# in that aspect. And as a result, what you have is, you don't have, if you're dealing with .NET bytecode, then you're fine, because at that point, whether you're using C# or F# doesn't really matter. But if you're doing something like static analysis, you won't have a lot of static analyzer for F#. So for us, we have to build our own, right? So we have a team dedicated, actually it's one of the teams I lead, and we have all the features in work, but what's the interesting aspect of F# code, or actually pure functional code, is because you don't have any side effect, you can reason the code really well, right? Because all my output would solely depend on the input. So techniques like static analysis tend to be a lot more effective in detecting issues in a functional code as opposed to object-oriented, because in object-oriented you don't know the state of the system, right? You can't just look at the system and reason about, because you don't know what the private values are holding. Same thing, we can talk about the security. The fact is that F# is not a mainstream language, so we have a problem with security tooling. Our solution is we have to build our own, so we have built a static analyzer and so on. And there's a security team that works on a lot of initiatives related to pre-commit and so on. I think for Scala, that's, I'm not sure if that statement is as true for Scala, because it's a relatively lot more used than F#. I know a lot of startups in New York, they tend to use Scala quite a lot actually. So anyway, so let's get back to, so I'm talking about benefits of F#, but because these slides were made for F#, but in reality benefits of F# is the same as benefits of functional programming. So you might as well substitute that benefits of using Scala. The concept would stay the same. Right, so you have three major parts: scalability, productivity, and code correctness. Let's actually look at all of them one by one. Scalability. The benefits of using immutability is that you don't have to worry about thread locks and all this stuff. So you kind of get infinite scalability. You can scale from, in this example, 30,000 to 2.5 million easily because your functions are pure. Right? Your functions are pure, you don't have any issues with scalability. It just comes, one of the major advantages of using functional languages actually is very, very easy to parallelize the code. This isn't something that you can say the same for Java, C# or even definitely not for C++. Okay, so benefits of using F# or Scala or whatever. Productivity. The code tends to be much more concise. I have some numbers, I think it's the next slide. But typically, the code tends to be a lot more terse. And if you think about it, CPU cycles are actually cheap. For an organization, it's the salary of the developer, that's the expensive part. So the developer has to write less code, means you can develop your software a lot cheaper than you probably would. If it directly translates to your costs. Lower code, terse code also means less to maintain, right? Less chances of bug, assuming you're using a bug-free compiler. So reduced ramp-up time for new developers, you have to read less code. Also, the way it's concise and clarity, it's very easy to write, actually understand the code, because functions are going to be pure. You don't have to go into complete depth. You can just see, okay, this is my event type, that's the function that outputs. Is a lot of time for us developers, actually, we spend time reading the code and debugging. And debugging is also something which is a lot simple. And reading is obviously something that's a lot simple, especially if you have less code to read. So I have some numbers. The numbers are for C# and Scala, F#. Scala is, I think, a little bit more verbose for F#, but this was actually taken from a website. So they re-implemented a C# project, right? And you can see the numbers on that table there. The code is about 1/3 the size, and null checks, and you don't really have nulls there. In F# we have something called options, and I'm pretty sure Scala has something similar. I don't know if it's called option or whatever it's called, but there's something. You don't actually need null checks within the pure code. You do need null checks when you use third-party libraries. So in F# you actually have, you can define tags on your function that this is nullable. So where you have the interface between F# and C#, you actually can say that this can actually hold nullable values, and then you have to add checks for that. But if you stay within the domain of functional programming, you don't actually need null checks. You can replace everything from options. And typically here F# code is 5 times smaller than C# code. Okay, so code correctness. I talked about debugging, so this is where it fits in. Strict typing makes writing correct code easy. The thing is that when you have your types defined, and a compiler would statically type check all, and if you have a violation, you actually would get a compile time error instead of having the runtime. Another thing, probably doesn't relate to code correctness as much, is I'm fond of writing compilers, by the way, in my personal time. And sometimes when I have to change the language which is right, I just change the type definition. The compiler is going to tell me all those places where I have to make the changes. So strict typing actually is pretty interesting. And immutability makes the code more predictable. Because, as I said, if your output depends solely on the input, you can reason a lot more about your code. You have exhaustive pattern matching. So exhaustive pattern matching means my type can have 10 different union cases. I have to match 10 different. If I have 9 but not 10, the compiler is going to compile time. So you're ignoring that case, it's going to break. Type system makes illegal states unpresentable. So you don't have the problem of state. I would be careful in saying you reduce the problem of state space explosion, right? It's not like you don't have it at all. And the possibility of system going to a state it cannot recover is going to be lot less. Before I proceed, questions, if any. Okay, so I'll go. Testing. So we divide our services into pure services and impure services, right? Pure services, the behavior is very predictable, so it can be tested exhaustively. For example, if you're testing something like ordering, the part that is going to be billing your credit card is going to be a separate impure service, and everything else will remain pure. So you can exhaustively test the pure services. For impure ones, you have to be a little careful with your test cases. But as a skilled programmer, what you usually tend to do is you tend to separate the pure part from the impure part and keep as little functionality as possible on the impure part. Your impure part should just be like basic I/O, right? So as much possible, keep your code on the pure services because they are very, very easily testable, highly testable. you would have the same story in an event-driven that you have the broker. So what you could do is, if you want to test one service, right, you can inject some messages and then you have an interpreter that would read. So the ordering service doesn't change it. You can actually even replace the message broker with some Kafka substitute, because you don't actually need an actual instance of Kafka, right, for test purpose. So you can inject the messages and then read the responses. So that's how you test services that are the event-driven, implemented as event-driven ones. Another big problem with microservices is traceability of your data. Like, how does your data flow? You have 1,000 services, you have an event, it goes somewhere, and it's hard to trace. So for that, we built a platform, we call it X-ray platform. So how it works is every event has an ID. So when service A sends an event, it sends an event, it also sends there's a particular Kafka topic that I received event ID and I'm sending this. When service B receives that, right, it looks at that ID and says, oh, I have received that event ID. And then you can take this information and then you can combine it and then you can graphically see how your data is flowing. There's another very interesting project. So this for us is a custom in-house proprietary stuff. But there's an open source version for the same. I think Uber was the one that developed it, and they call it Jaeger. Although it has nothing to do with functional programming, I think it was implemented in Go. I'm not too much familiar with what they have done, but based on my understanding, it's actually something pretty similar to what we have done in X-ray, right? Essential problem we are trying to solve is how is the data flowing through the microservices. We also have SLA monitoring. We call it pulse services, right? So, so customers have tight SLAs. You want to service a request within a certain fraction of time and so on. So there are different metrics that the New Relic monitoring service would send. We have the pulse service that pulls these, stores this, and then you have a dashboard. We were using Looker, now we are using Grafana, which are trying to move. And then you have different rules that when you query the data, they are computed and they say, okay, fine, if my requests are taking more than 50 milliseconds for 95% of the time, I have a problem. So you get alerted that your microservices are behaving in a fashion that they should not be. There's something wrong, and the PagerDuty stuff would alert the person concerned and take the appropriate action. Also unrelated to functional programming, but we do this a lot. There's a new discipline called chaos engineering. Sorry? Yeah. Different people have different terms. I think Netflix was the one that they are the pioneers in chaos engineering, right? I think some banks, they call it Symbian Army. Some call them, they're different names. What chaos engineering, this is a textbook definition of chaos engineering, right? It is an experiment, so on. But the key characteristic of this is that you basically inject failures in the system that mirrors your actual failures in the real world and see how the system behaves and recovers. So for example, think of all the distributed systems failure modes, right? You can have a data center go down, you can have a network failure and so on. And you simulate that by saying, okay, what if I switch off all my virtual machines that are on my east data center and just leave the west ones running? How does my system behave? So in an ideal world, your system should actually recover. And if it doesn't, you've identified a weak point. So how chaos engineering in practice works is that you have the steady state of a system behaves in a certain way it should be, and then you identify all the different events that could possibly happen, like data center failure, network going down, hard disk failure, so on, and you simulate these chaos, the term they use is chaos, these events that warrant a description, and monitor the effects on the system. And one of the two things will happen. System recovers, so yeah, you're confident that in an event where the actual production goes down, actual failure happens, you will be able to recover. And if it's not able to recover, you have identified a point of weakness. And I think historically what happened was that Netflix actually, during the prime time, Christmas time, the services was down. and they lost a lot of revenue. So they were like, how do we come up with better ways of testing such scenarios? And very recently, I think it was 8 months back, AWS East, I think S3 service went down. And there was a chaos in the east coast of US. We were in AWS, so we were fine, but a lot of people weren't. And essentially, these are the kind of scenarios that chaos engineering actually can help you solve, right? They can basically build resilience in your system. So if they would have used it, they would have been fine. Unfortunately, they didn't. Anyway, so distributed scheduler. This is Nomad. We use a distributed scheduler called Nomad. Part of the reason why we have to use Nomad is because we are a .NET shop, so there are limitations on that. But going a little bit broad, you would have some kind of multi-region, flexible, scalable schedule. I think you have a lot of choices in the Java world. Kubernetes, container management, Meetup, and so on. So these are tools for managing a cluster of machines and so on. And essentially what they are doing is your infrastructure is modeled as a code, right? You have stacked away all the physical machines and locations, and you model your infrastructure more as a declarative style. There's actually a pretty good book with the title Infrastructure as a Code, and I'm forgetting who the author is, but
Keith Morris.
Yeah, that one. That's actually a good read that talks about a lot of this stuff. Okay, so I'm coming back to end conclusion. Very few startups, like I said, actually, the truth is that nobody has scaled that fast, but I generally don't make these statements because they tend to be very controversial. And somebody will say, no, I know this one. So I generally say, I am not aware of any company that has scaled so fast. So if you do come up with an example, I don't look bad. But anyway, so we grew from I think we reached the unicorn status within a year and a half. A lot of scalability and productivity gain we got was due to F#. I think we are industry's largest commercial user of F#. And I'm pretty sure I'm correct. I read this somewhere, and nobody uses F#. I mean, there are a lot of open source projects and so on, but it's one thing is doing an open source project, another thing is running a multi-billion-dollar company, right? Nobody does it on an F#. And one of the characteristics was we had this architecture which we built, and it has actually been unchanged since the start. So it tells us that we did a very good job architecting our system. So I'm at the end and I'm ready for questions.
Cloud providers provide some sort of chaos to your systems?
So the question was, does cloud provider provide you chaos? Answer is no, because this is very much dependent on your application, right? So cloud provider would provide you a programmatic API to shut down your resources, but that's all it can do. It doesn't know your application, in what regions you are hosting and so on, right? So you basically would have to understand what are the different failure modes that you could have, and you have to write code to prevent that in your chaos engine.
Yeah, but maybe for networks working or whatever, package loss.
Like cloud providers can only do up to an infrastructure level, right? But they don't have the information of connectivity. You have a network failure, but what information would that network carry? Cloud provider doesn't know, right? That's your application specific. So cloud provider can at best say, okay, fine, I will give you an ability that, if you shut down, I will notify, I can monitor. So they can give you a monitoring. They do actually have a monitoring and telemetry and all that stuff. But if you really think about chaos engineering, I don't think that you don't really deal with the infrastructure level, and it's not something that your cloud provider can do much about it. You have to do it yourself because it's application specific.
So you separate stateless and stateful services and try to make stateful services as minimal as you can.
That is correct.
So maybe C# is a better choice for write these stateful services because C# is an imperative language, or you use F# also for.
Okay. So I'll repeat the question. The question is that we talked about separating the stateful and stateless, and the question is, do we use C# for the stateful ones, or do we use F#, and is this better or not? So the answer generally is it's better for you to use one language or as little language as possible. You don't want a jumble where you have some part of it C#, some part of it F#, some part of it VB. They can theoretically interchange, but generally we'll try to use F# for everything. Now, F# does support C# object-oriented programming, right? By definition. So whatever you can write for F#, you can actually write. Whatever you can write for C#, you can actually write for F#. We generally would try to use F# in almost everything. Only in cases where we are, somebody wrote some C# code and we want to use that code and then we are not going to rewrite and so on. That's the only place where we will use F#. And I think the support for ASP.NET in F#, there are some limitations. So if you want to use ASP, you probably will have a C# layer calling your F#. That's also another place where we use C#. But generally, you can write all the impure code that you can write with C# in F# also. I don't really have examples, but there's a very good website, F# for Fun and Profit. And if you go there, they actually, what they do is they have the C# code on one hand and they have the F# code on the other hand. So you pretty much can do everything that you can do with C# and F#. And I personally don't think it's a good idea to make a polyglot systems and hodgepodge with using multiple languages. So no.
But one of advantage of microservice architecture, that you can write your services in different languages. So you think it's not advantage. So you should use only one language for all services if you can.
Okay. So microservice architecture allows you to write, right? But that doesn't mean you should do it just because it allows you. It's the same thing as saying F# allows me to use impure programming, but that doesn't really mean I should be, right? From a developer point of view, imagine you're training your developers into an F#, and now you have to write C#, right? Because from an organization and administrative point of view, you would have a problem. If there's a strong reason why you want to use it, microservice architecture allows you to do it, but I would still be careful in, just because you have a freedom, don't just abuse it to any extent. And you have to use your sound engineering judgment. What is it that you're using C# for specifically that you can't do F#? I mean, I can write pretty much everything in F#. It's not like C# code is going to be any better because it gets translated to the same intermediate language. I know F#. If I have a problem, I can ask other people because here everybody's an expert of F#. So it doesn't really justify me to, I can do it if I want to, and yes, microservice structure allows me to do it, but there's no reason for me to do it. More questions? Yes, sir.
What's the right size of microservice? Do you base it just on aggregate, or how do you decide about the size?
Okay, so the question is, what's the right size of microservice? And unfortunately, I don't have an answer. And I don't think there is an answer because this is a very empirical definition. Generally, you tend to follow a single responsibility principle. I mean, you would try to focus on one specific thing, okay, card or an object and so on. And it's the same thing as how do you decide in an object-oriented programming, how do you refactor your classes, right? You apply the same single responsibility principle. So, so try to have specialized reusable components that you think will be used across the system and separate it out as a microservice. But I don't have a hard and fast definition like, your code should be 1,000 lines of code or something. I don't think those things work really well.
And the example of card is
card is an object more, if you were to model card is more of an object than a service. A service is essentially a function. So I would say what are the functions you can do in a card are going to be your services. Probably if they are closely related functions, you can have 3-4 functions as one service depending on the size and other factors, or you could possibly, see card is basically a data that actually will flow between the service. But they are not really modeled as a service, right? So think of it this way. You have a function and you have a data flowing between these functions, right? So cart is the data part. I would say cart means process a cart, ship orders in the cart. Those are services, yes. And they would be modeled as separate services, like shipping service, order management, something like, when you as a user gives me a cart, you give me all the items, but those all the items may not be from the same merchant, right? Somebody has to separate out, okay, this item is from this merchant, so I should notify this merchant, this item is from another merchant, and so on. So there will be an intermediate service in between. Then there will be a service there for each merchant. It will, okay, pick up, ship, so on, and then, process all those things. So functions to a cart are services, not the cart itself. Question? Yeah.
Do you have single repository, or do you separate
Okay.
different repositories? And if so, do you notice any code duplication across repositories?
Okay, so the question is, do you have a single repository or do you have multiple repository, and we notice the difference between? Well, this is actually a very debatable topic. Right now we have a hodgepodge actually right now, honestly speaking. We have several repositories. We don't have one repository. We would want to use one repository. So we want to use monorepo. Our senior vice president of engineering, he's quit now, but he used to be from Google, and he's a big fan of monorepo. Google does monorepo. The problem with monorepo is that in terms of tooling, monorepo is not that easy to implement, right? You need to have a very sophisticated tooling for monorepo. We don't have that tooling yet, so no, we cannot do it. Now, Microsoft started a project. They call it a Git virtual file system. So if you Google that, you actually see how. I'm not too sure of what they actually do, but I believe they combine these different repositories as it behaves virtually as one repository. So they potentially you could use monorepo like that. We are exploring that possibility, but again, our problem is that the tooling required is too much. So it's not an easy transition now. In terms of changes and so on, I mean, one of the big problems is that what if you change the contract, right? That's where, in monorepo, you have this advantage that you get the atomicity of a commit. So if I change a contract, I build my entire system, right? All the places where that contract is violated or is still using the old version of contract will break during compile time. Whereas if I have separate repos, that usually I won't be able to detect it. Although you can still build the tooling in the sense that, build all the repos and so on. And we are somewhere there where we have limited amount of tooling. So yes, I mean, monorepo definitely, if you can successfully, in my opinion, if you can successfully implement a monorepo, that's a good thing, but implementing a monorepo is not at all an easy thing. The second thing is, you may have an atomicity of a commit, right? But you don't have an atomicity of a deployment.
That's what I was going to ask. Is that the tooling that you're missing?
It's not a tooling, it's actually by design a problem, right? Because you want to reduce your downtime. So if I have an atomicity of deployment, then deploying all those things that shouldn't be deployed. Now there are ways in which you could solve that problem, and one of the ways we are exploring is you build these binaries. So we'll build all the binaries, and then we calculate the hash for those binaries. And we know what's running in production, and we keep track of the hashes. So if the hashes don't change, we don't deploy, right? But again, it's not as easy when you actually practically implement it, so we don't do it. And if you look at the current ways of doing using Jenkins and all this, it's not easy. So it's great to have it, but we are not there. One by one. Yes, sir.
Do you have integration between your business metrics and your orchestration server, and what do you use for orchestration?
I'm not sure if I understand your question, sorry.
So, what do you use for doing the orchestration of all the management of microservices?
There are different ways of doing it. We actually don't have the distributed scheduler to do that for you, right? It's what it's supposed to do. They have alternatives. I think Azure also provides Azure Service Fabric to do all the orchestration part, but we didn't use it because I think it was too expensive to use it. So there were economic reasons.
Okay, but my question was that how do you fulfill the business needs in terms of upscaling and downscaling with your current orchestration server?
There is no direct way of doing it. What you would do is you would measure the metrics, right? So I can't say that I need a 4.9 availability and I should orchestrate in such a way that I get it. I can't do that. That's not an easy thing. I know Google does it using concept of error budget, but how we tend to do it is we have a more manual way of doing it. We measure the uptime and downtimes, and then we know how much, to what level we do orchestration. It's not an automated system. It's actually pretty manually driven. There was a question from the yes.
Thank you for the talk. I really liked a lot of your reasoning why you like F# very much, and I can really appreciate that. From a scala from 1 to 10, what is your self-estimation about your previous experience in object-oriented programming? Did you do some kind of greater work in it?
You mean me personally?
Yes, you personally, and your own estimate of 1 to 10, how good you are in object-oriented.
No, on a scale, not in a scala. So you,
Yeah,
in a scale. So he's not talking about scala, he's talking about the scale.
An object-oriented?
Right.
I did considerable. I didn't use a lot of Java part of it, but C# part probably say 7, 8. I used to do fair amount of object-oriented programming. In fact, Jet is the only place which uses functional programming commercially. So when I joined, so after my PhD, I joined Microsoft, and they were using C# for everything. F# obviously was made by Microsoft Research, but it was confined to research. So my interest in F# actually, they have a concept of what they call as Microsoft Garage, which is something similar to Google 20%, but not the same as you have side projects and Microsoft uses resources. So my interest in F# actually developed through one of those garage projects and through Microsoft Research. So my daytime was C# and nighttime was F#, until I joined Jet, and then daytime and nighttime they were both F#. But yeah, I mean, I've done a lot of professional object-oriented programming to a reasonable extent.
Thank you.
No problem. More questions? Yes, sir. Let's move, then I'll continue. Yes.
I was wondering about your error handling strategies with your event-driven services. If you run into problem handling individual events.
So the question is error handling using event-driven. Well, for synchronous ones, it's really easy, right? There's nothing much to do. For asynchronous, it is a problem. That's actually, if you make an asynchronous problem, you don't have a traceability. So yes, generally, typically you know that if the X-ray is sending all the information on what services IDs are going. So you do have a little bit of traceability information in the sense that order management sent an order with ID XYZ and event manager is not picking it up. So there's something wrong. There is no direct way of handling that kind of error. You have to build a little bit of tooling and monitoring and so on because you're logging services continuously, right? So from logs you see that there was an order ID that went there, but the service didn't really pick up that order ID. There's something wrong there. You can infer those, you have to handle those errors indirectly, not directly. You can't do a direct one.
I didn't mean like from the actual infrastructure point of view, but the application logic point of view. So you're talking about the case of, a consumer is stalled, whatever. I'm talking about actually a bug in the software where something goes wrong handling that.
Well, you have try and catch.
Sorry?
You have try and catch statements all around. You can do that in F# as well as as much as you can do in C#. It's a little tricky to do it in Haskell, which is purely functional, because it cleanly separates out the pure and impure part, but F# being mixed, you can encapsulate your code and try and catch statement pretty much the same way you do in C# and you can do error handling that way. So there's no problem with that. Yeah, there was one question and answer, yes.
You said you use the event-driven architecture a lot. Do you sometimes feel the pain that you don't know what happens when you put an event in the event system, and you have this X-ray system, but with this,
Yes, there is a
then
pain.
you only see one event for one specific event, and that this event could change if there are other inputs?
So the question is about pain using event driven. First of all, I don't think events change. Right? Events by definition is immutable. Now, one event could generate another event. So the event itself doesn't change, but you have another event generating. Like I said, traceability in a distributed system with a lot of asynchronous requests is a hard problem. So yes, there are pros and cons of event-driven. Sure, this is one of the cons, and yes, we do feel the pain. But then there are pros also, right? And the decision you make is that the benefits outweigh the cons. Then you use it. The scalability and how your system evolves. Actually, when you're a startup small, it may not make. But as the organization grows, right, how it evolves, there are huge advantages that will offset this a disadvantage of traceability. You don't have a lot of insight, but then you do have platforms like X-Ray that helps you gain that insight. So it's not that big of a problem. It is a problem, but it is a manageable problem. Yes.
So you said yourself that asynchronous error handling is a problem. I didn't get that really, because where is the difference between an error and an event?
So when I say asynchronous, I wasn't talking exactly from a code point of view, but let's put it this way, that you send an event to your broker, right? You don't know what happened after that. So because in this mode of communication, it goes through an either and then you have no way of tracing. Whereas when you send a request, right, you get a response back 200, 400 or something.
But if the response is an error, or the event which you get back is an error event, where's the issue?
There is no issue, but the question is you don't get it back. If you're using something like Kafka, if I inject a message, I don't know what happened to that message once I inject it. I mean, I get an acknowledgement that the message has been put to broker and has been distributed to customer, yes, but what if it was wrong? What if the message was formatted? Not formatted, but let's say you're ordering a number of items in a cart and there has to be an integer. Sure, it's an integer, but it is -5, which makes no sense. How do you find that problem? What do you do with that problem, right? So those are the problems that are not easy to solve.
So because you don't get any kind of event back, which tells you -5 doesn't make sense?
Not directly. You would, fine, you would have a service A that will process it and then you will have it in logs and so on. And you do get it, but you do get it indirectly. You don't get it real time. You don't get it at that point.
You don't get it back to the guy who caused it. But
at that point of time, yes. You do get it later on, yes.
Exactly, and you finally find out
who
is the guy who had a problem as a consumer with the producer.
True, so it's more work. I mean, I'm not saying it is a problem. I'm not saying it's so much of a problem that you cannot solve it. It is a solvable problem, but it is still a problem. Yes, sir.
Do you develop best practice for changing or evolving events? So, for example, the event changes. Do you introduce a new event, or are you trying to version it?
First of all, event changing is something that you should be doing very often in the first place, right? So the best practice is don't do it if you don't need it. That's the best practice. Now, if you do have to do it, there are multiple ways. Versioning is often a good one, and we generally tend to do versioning. But also, what we try to do is that we don't have a monorepo, but you would try to build the entire project, right? So statically, your compiler is actually, if you change the format, your code is going to break on other services also. So you could possibly do it directly with compile time. But yeah, I mean, you should, the best practice is to do it as little as possible, and when you do it, exercise a lot of caution. Again, it's a solvable problem, but it is a problem.
You mentioned that you had a really big systems, and I imagine that it had a lot of events going on.
Oh yeah, of course.
So then I also assume that you had aggregate routes, which actually were based on a lot of events. And at some point in time, you have to do, we call it replay those events into the domain model. And we also did a system and sometimes this got really slow. How did you solve that?
Okay, actually that answer to that question is one of the links that Christian actually posted. You have a method of snapshotting. So you don't replay your system from, if your company started 10 years ago, I'm not going to replay the system 10 years ago, right? I snapshot it. I snapshot it for 6 months, 1 year, whatever, and so on. You build the system. There's a possibility that now you have two sources of information. One that you actually get by pulling your event, and another is your snapshot. And ideally, you should not have a discrepancy. But there is no guarantee, and yes, that's a drawback that you have to live with.
Maybe there's some new magic, I don't know.
I don't know of magic. Actually, I don't know of any magic anywhere, to be honest with you. But yeah, snapshotting would be the way to go forward. And you can decide the frequency of snapshotting because now there are pros and cons, right? If you snapshot too fast, then you are incurring a performance penalty, and if you snapshot it too less, then each time you have to actually get a state, you have to do too much of work. So there's a fine divide there. Yes.
So Christina was talking about sourcing. So you use Kafka, but Kafka is mostly like a log. And if you are the .NET project, maybe you have tried Event Store developed by Greg Young.
We do use Event Store, yeah. Yeah. So we use a lot of stuff. I can't give you a list of all the stuff we use. We use Event Store. We use I think there's a service bus also that Azure has it. We use Kafka. Kafka is our tier 2 system. Event Store is tier 1. I think one of the problems that Event Store has, it's not very scalable. Yeah, that's a problem. Because if you look at the CAP theorem wise, I think Event Store is not is like CA probably. It does not support partitioning. So what we are doing is we are actually building a replacement for Event Store, which is geo-redundant. And the link that Christian has, if you read the last paragraph, it actually talks about it. Yeah, more questions? Good, yes.
With many services, how do you do security or authentication between them? Do you?
Why would we? If they're running in our subscription, once the data enters in our subscription, it's the cloud provider's responsibility that our subscription is isolated. There won't be a lot of security between the services within one cloud subscription, right? Because you're still within the domain, you're still behind the firewall. Any more questions?
Cool.
Oh, this one.
Yes.
Thank you for talking to me. I was wondering, you talked a bit about, let's say, events going. Yeah, in the future, events are going to be changed at some point in time, maybe. So they will be versioning is one way to approach this. How do you actually deal with this? So with versioning of events and also possibly of microservices.
So there are actually two different questions. I'm going to answer the first question. So how do you maintain the evolvability of events, right? Obviously versioning is one. And the second thing is you have what is called as a tolerant reader. In the sense you have a reader which can, if certain attributes are missing, it can take a default. It's not going to penalize you. So you do have a tolerant reader that can that kind of reads between too much of you can read across the versions of event. Obviously you have to be very careful because you can't just change it's the same thing as backward compatible, right? You don't change an API out of the side, right? It's a decision that you make really, really very carefully. And yes, it's a problem, but with careful reasoning you can actually minimize it. And and using versioning or using tolerant, you can actually reduce the instances to near zero where you face such a problem. The second part of the question is how do you evolve microservices, right? Now, if your contract definitions don't change, why is it a problem evolving microservices? I mean, your microservice is independent, right? The only problem comes when your contract definitions change. That's where the evolvability problem comes, and they shouldn't change as much, so you don't have that frequently. And B, then you have to I mean, there was a question on monorepo, right? Things like monorepo helps. Otherwise, you have additional tooling that you have to build a lot of simultaneous and make sure that compile time, and when you deploy it, you have to also deploy it carefully, because if you change one contract, you actually would have to deploy probably 20 services that depend on that contract. And there's a lot of static analysis tooling that actually does that to solve that problem.
So I would like to wrap it up. Hopefully you stay around for another beer.
Yeah, now the thing is, I'm not